I wanted to make a quick video to explain some of the concepts that we went over in class the other day about splines using a new and more refined Grasshopper definition. Um, I will provide you with these files, but here's a little bit about how to go through and interpret the material. So right here, this is the Grasshopper definition to produce the compound arc. We have a start point, so you went pink, endpoint, start vector, and you can see that if we change the vector, right, of the start, uh, the whole curve updates. Because to get the end vector, we don't supply that. That's something that's just going to result from creating an arc with this start point, this end point, and this starting vector. And then we evaluate the curve over here to give the new start vector for a second segment, right, which is this one, right? So the only inputs to this whole system are the things circled in yellow, a start point and end point, which becomes a new start point and a new end point, and a start vector only at the very beginning. Contrast this with a compound Bezier curve like you would find in Illustrator, right? So here we have a start point, an end point, and we also have a start vector and an end vector, right? So in this case, this curve is determined by 2 points and two vectors, two tangent vectors. And then to get the tangent vector uh, at the start of the new curve, we essentially just take the reverse of the vector that we used for the endpoint of the previous curve, right? So that's easier to see intuitively than to listen to what I said. So there you see, right? Here's one, here's the vector, that's the start point of the new curve. And then this vector here is, oops, here we go, is uh, is the last input to the system, which is an end vector for the endpoint, right? And that gives you a Bezier curve, a compound Bezier curve with two segments with continuity right here, right? So then the next thing uh, that I'm demonstrating here is a B-spline, which is actually a generalization of a compound Bezier curve, except this B-spline is controlled by control points, right? So once again, you move the control points, the curve updates, and this rainbow here is demonstrating uh, what happens when you use the same control points to construct a B-spline with different curve degrees. And what curve degrees, that means how many control points affect any given point on the curve. So in degree one, right, that always gives you a polyline with kinks. Degree two, it means that any point along here is going to be controlled a little bit by that point and a little bit by this point. Or any point along here is going to be controlled a little bit by that control point and a little bit by that control point. If you have, let's say, a higher degree, it means that a point along the curve right here is going to be affected by more control points. Um, and so uh, that is um, that's a B spline. Now, the the next thing that we're looking at is a NURBS curve, or a NURBS spline, non-uniform rational basis spline. The B in B spline is basis spline. So the only difference between the B spline and a NURBS spline is that we add the idea that each one of these control points can have a different weight. right? So one way of thinking of the B-spline is to say it's a NURBS curve where all of the control points have the same weight. But what if they don't? What if they don't all have the same weight? So here you can see in this degree 3 NURBS curve, right? I'm showing the same degree 3, but I'm showing the first one as having, which is this one, right? Is what happens when I'm giving equal weight using the NURBS curve uh, component. And you can see if you turn that on as well, right? Those two curves are the same. So the B spline and the NURBS curve, where the list of weights is exactly the same, produces the same curve. But if we do something like this, where we say, what happens if the fourth point, 0, 1, 2, or 0, 1, 2, 3, which is this point, has a weight of 0.5. And you can see that what's happening is it starts to pull a little bit more towards that point. Right? Down here, we're saying what happens if everything has a weight of 1 except for this point and it has a weight of 9. Right? And you can see what's happening in the pink spline here, right? It's pulling way more towards this one. And you can also see that that pull is still affecting the curve going beyond. So finally, right, same experiment over here, except over here, we're looking at a degree 5 as opposed to a degree 3, which means that any given point along the curve is affected to some degree by more control points. So for example, right, if we move this, if you watch very carefully, you can see, right, that the curve sort of moves over here, but this part isn't changing, right? When I move that, keep your eye on the left, right? It isn't changing. Whereas over here, if I move this, you get more movement in this part of the curve being affected by that control point because this is a higher degree curve. This is a degree 5 curve. So hopefully if you go through this definition, you play with or these definitions, you play with them yourself, you'll get a little bit clearer understanding of the difference between arcs, Bezier splines, B-splines, and NURBS curves, an understanding of curve degree, and of control point weight. And lastly, to understand that a Bezier is really just a special case of a B-spline, and a B-spline is really just a special case of the NURBS. So this last point, this is kind of a sort of historical explanation down here, is we look at the Casteljau's algorithm. Um, and you can see here the input is these control points, right, which we can connect with the dark purple. And when you go to the definition here and you slide the slider, right, I'm looking at where we evaluate each of these segments. So if I set that to 0.5 approximately, right, you're getting about the midpoint of each of these segments. And then we take these points that come from the midpoint of each of these segments, right, and we make that our new dark purple line over here. And then we take the midpoint of each of those segments. And then we keep doing the same thing, same thing, same thing, until we end up with just one point, which is that point, right? And when you move the slider, you can see, right, how that one point sort of moves in space. And you realize that depending upon where you evaluate your original segments, you're kind of tracing out a new spline. So down here, we're doing exactly the same thing, except instead of evaluating at one point, we're evaluating at multiple points simultaneously. And this slider will change how many points, right? So if I set it to 3, right, we're evaluating essentially, well, actually 2 points, but So there's, that one and that one, the 1/3 and the 2/3, right? If I bump that up to 4, we're getting 3 values, 1, 2, 3. If I bump it up to, 12, right? We're getting 12 values along each of those segments. And then we're doing the same thing where we repeat the same process over and over and over. But you see that what we get at the end here when we have 12 points, right, is we're getting these points. And if we connect the dots with the green line, you can see, and it's at this point over here where I take my original control points and I move them over and I construct a B-spline, which is a NURBS curve, where all these control points here in white are given equal weight. And you can see that the curve that we end up with is quite similar to the green curve that we're getting from de Casteljau's, pardon my French, algorithm, and that the more we slide the slider with more divisions, the closer and closer and closer we get to what is essentially a B-spline. And you might ask, well, what degree, right? What degree B-spline? Um, and the answer in this case is the degree, which I'm inputting right here, is essentially the number of control points, which in this case is 1, 2, 3, 4, 5, 6, 7, 8, minus 1. So degree 7. So a degree 7 B-spline, meaning every point is affected by every control point to some degree, right? That's what you're getting as the output of the Casteljau's algorithm uh, when you use lots of different subdivisions. So hopefully this is something you can play with, and it's another way of understanding the material, making it a little bit more clear so that you can understand what somebody's talking about when you're talking about something like an arc or another comic section versus a Bezier curve, a B-spline, or NURBS. And it gives you a little bit of a sense and demystifies these things just a little bit.